Reversible reactions and equilibrium. So reversible reactions, basically when we have a forward reaction here, and we also have the reverse reaction. So not all reactions are just from one left to right, as in this case. In fact, most reactions really can tend to be reversible under the correct conditions. So that means the product can go back to the reactant, and we signify that with a double arrow. So if we look here at the reactants, if it's just SO2 and O2, it's not equilibrium. If it's just the products at SO3, it's not at equilibrium. It's only at equilibrium when the rates of reaction, when it goes back and forth between SO2, O2, and SO3. Chemical equilibrium here we denote by a double arrow, or one of those, or we can also have one of these. So that means chemical equilibrium when the rates of the forward and reverse reactions are equal. So that means the speed of going to the forward reaction and then the reverse reaction, the speed. So no net change, net change will occur in the actual amounts. Once a reaction occurs and stabilizes, then we have equilibrium. So let's look at an example here. Let's say we have a school. There are students outside, and then maybe there are some teachers, faculty. So they'll come in. Now, it's not until later when we have amounts of the students and the teachers here in the school. Now, equilibrium is reached when the net amount is the same. So the coming and going are equal. So let's say about 10 o'clock, everything kind of settles down. So this is at 6 a.m. This is at 10 a.m. and everything settles down. Most of everybody is inside the school, but then we have some stragglers going in and out. And depending on the time, we can say this is 1 p.m. over here. Depending on the time, we're going to get basically the same. It might be different students coming and going and different teachers coming and going, but we're going to have the same basic amounts coming and going. Again, they might come and go, basic amount. It's an equilibrium. Now notice, it doesn't really have to be equal on both sides. There's more students and teachers on the inside than on the outside. Equilibrium does not mean the sides are equal in amount. What it means is the rate of change is the same. There's no net change. We still have 3 students outside and 30 students inside. And we can denote that by, and sorry, this is blurry, probably your vision, so you might need to get the glasses. Again, we have the double arrow, which means that equilibrium is reduced, but this means that most are in the reactant phase. Most are A. But it's still, some are B, some go to B. 1% will go to B, and vice versa here. Most are B, but then some will go back to A. It just evens out there. It just levels out. It's all chill. Now let's look at these graphs here. The rate versus time. So at equilibrium, when all the rates are the same, so remember that's basically speed. The speed of the forward reaction here is equal to the speed of the reverse reaction. And everything kind of mellows out. Down here, the amount, even though notice here we could have less reactants, which is fine, more product when there's no change in amount, when it equals out, so there's no change here. That's why we have the level line, there's no change, then we have equilibrium. This is LeChatelier principle, or Henri Principe de LeChatelier. From Henri LeChatelier, he came up with some principles about stresses on a reaction and the rates of reaction and how stresses on a reaction affects it. So what he said is if a stress is applied to a system that is in equilibrium, that system will change to alleviate the stress. If a system at equilibrium is disturbed, the reaction will proceed in one direction or another in order to reestablish equilibrium. The reaction is already, it's cool, it's chill, but something happens to it, it's going to shift so it goes back to equilibrium. Just like if you're driving a car and you have to swerve for some reason, you're going to have to swerve back. So you swerve to the left to avoid a squirrel in the world, you're going to swerve back to the right to get back on track. Reaction does the same thing. If something happens to it, it's going to change back to where it was. So what are some examples of stress? What is a stress? Well, stress is a change in concentration. We have a change in temperature or a change in pressure. Now we are talking about aqueous solutions and gases here. Pure solids and pure liquids really have no effect on equilibrium. So a change in concentration. Notice here we add CO2. We add CO2 here, the direction of the shift is going to be to the left. If we remove CO2, we're going to go to the right. The effect of changing concentrations, if we add reactants or products, if we increase the concentration. If we add reactants or products, we're increasing the concentration, it will shift to the other side. So if we add reactants, we have reactants and products. If we do more reactants and give more reactants, we'll shift. It'll start making more products. If we have more products added, it'll start making more reactants. So it shifts the other side to compensate. So an example here is, let's say we're making bologna sandwiches. We have bologna here, plus the bread, and we have our bologna sandwich. Tasty. If we start making or adding more bologna, said, hey, we just went to the store, got some bologna, and we got some bread. We got twice as much bologna and twice as much bread. We got a deal at Costco. Well, now we start making more sandwiches to compensate. Now, let's say in the opposite scenario, we have all these sandwiches, all these bologna sandwiches sitting around. We're going to compensate by, well, we don't want all those bread sandwiches sitting around, so we're going to take those apart and just keep them ready for when we need them. We'll take those sandwiches apart and keep them until we need to make more sandwiches. So the shift is always to the other side if we're adding reactants or products. Now, what about if we remove product or reactant? Well, then we have a shift to the same side. If we remove reactants and products, let's say we remove some of these reactants, well, the shift will be back there to compensate. The products will start making more reactants to compensate. If we remove product, then we're going to shift again to the products to start making more product. In the sandwich analogy, let's say we have bologna and bread again. We have our sandwich here. If we remove that, now if we remove the product, someone comes in, sees white bread, bologna, tasty, the shift will be to the product. More product needs to be made to replace it. So we'll start making more product, more bologna sandwiches. If on the other hand, we've run out of bologna and bread, and we got all these sandwiches sticking around here, we're going to shift that and take some of those sandwiches and take them apart and make more just bologna and just bread, just so we have some of that in case someone wants some other types of sandwich, for example. What about a change in pressure? So we can see here, here we have equilibrium, it's just chilling, everything's going well. Now, equilibrium is disturbed. We increase the pressure by decreasing the volume, so the pressure goes up. And then what's going to happen is the equilibrium is going to reestablish itself in a way that can lessen that pressure and get back to where it was. So the key thing here is before there was 11 gas molecules, and now we have 9 gas molecules. So whatever we could do to decrease it, so that means the increased pressure caused the shift to have less gas molecules, because if you remember, if you have less molecules of gas, it'll have less pressure. Now if we reduce the pressure, it will go this way. So how does this affect us? So increasing the volume, which means decreasing the pressure. So think of increasing the volume of a gas will decrease the pressure. It shifts to the side with more moles of gas. The higher number of molecules will result in more pressure. So what does that mean? So let's just look at a made-up example here. If we have 3x2 plus 2y goes to 6xy, and we increase the volume, which decreases the pressure. We gives them more room to run around or roam around. The shift will be to the one with the most gas molecules, which would be the left side. This has the most gas molecules because we want to keep the pressure the same. And the most gas molecules, the more gas molecules there is, they'll have more of a chance of keeping that pressure the same. If there's more gas molecules, it'll exert more pressure. So the shift will be more to the left. What if we decrease the volume, which means we increase the pressure? That will shift to the side with fewer molecules. That means it's going to shift to the right. This has fewer molecules. That means it will exert less pressure. So we're trying to get back to normal. What happens when the changes in volume have no effect? Well, that happens when the molecules are the same on both sides. That means they'll exert the same pressure no matter what. In this case, the change in volume will have no effect because the change pressure will have no effect. So what if we change temperature? Now let's look at an endothermic reaction. So remember, in an endothermic reaction, we have reaction plus energy. We have to put energy into the reaction side to get the product. So if we increase the energy, that means it's just like increasing a reactant. It's going to shift to the product side. We're going to get more product. The same thing is if in an endothermic reaction, if we remove some of that energy, we just add a little bit of energy, it's just like removing a reactant, the shift is going to be to the left side. Okay, let's say we're making some bread and we've got our ingredients here, just kind of flat, just lays there. We put it in the oven, give it some energy. Let's say we bake it normally at 300 degrees Fahrenheit, we'll say, and then we get a nice loaf of bread. But then we boost up that to 500 degrees. We're getting more energy. We're going to get more product. Let's say we take some of that energy away. Instead of at 500 degrees, we just do 100 degrees. You know, it's not going to really cook well. So we're going to get less product. The shift will be back here. We will get less product. The shift will be back to the reactant. In an exothermic reaction, remember, the reactants will go to products and we'll get some energy out. So we can think of energy as being like an extra product. If we increase the energy of the product in an exothermic reaction, if we increase the energy, that means it's like more product. So that means it's going to shift to the left, more reactant. If we reduce energy, not as much energy there anymore, we're going to make, it's like less products, we're going to make more of those products. Trying to keep things in equilibrium, it's going to shift so more product will be made to get more energy there. Okay, for example, let's say you have match, lighter fluid, and wood. And we're going to get a nice fire and some heat here, some energy. Okay, so let's say we have all this stuff, the lighter fluid, matches, and wood all stockpiled. And let's say it's a really cold day out. It's freezing out. It's winter. So that means there's not much energy out there. So the temperature is low. Temperature is low, there's not much energy, so we're going to start burning more firewood. We're going to start making more of this. We're going to start burning more firewood. We're going to start burning this stuff so we can make, or the shift will be here. There's less energy. We need the shift. We want to make more energy here. We're going to get more warmth from that fire, so we're going to start reacting more here. The match, the firewood, the lighter fluid, they're going to react more so we can compensate for the cold temperature outside and make more energy. Make more exothermic reactions so we can have more heat. Now, by the same token, let's say it's really hot out. It's a hot summer day, sun shining. We have exothermic reaction here. We have a lot of energy out there in the air. The shift, we have a lot of this. The shift is going to be back to the left. Because what we're going to say is, well, you know what? We don't need to make as much. We're going to kind of stockpile this stuff. So We're just going to kind of keep this stuff on hand for later. The exothermic reaction, there's so much energy out there already, so much more temperatures that we can just chill out with our burning. We'll just keep our matches and lighter fluid and wood all to ourselves. We won't burn it yet.